Bom, vamos então. Eu antes de hoje talvez apenas vá falar um pouco do tipo de modelos que vamos falar durante o curso. E eu preparei algumas referências que eu vou dar para vocês os dois. E deixem-me só, já que estão a gravar, eu vou só ler quais as referências, mas podem me perguntar também, ou vocês podem colocar na alguma página se tiverem acesso. Mas o que eu sugeri foi o curso do John McGreevy, um livro chamado Introduction to Normalization Group Methods in Physics, do Pedro, Statistical Field Theory, do Paris, Statistical Field Theory, do Sardo, Executable Models in Statistical Mechanics, do Baxter, Statistical Mechanics, do Feynman, Statistical Field Theory, do Witzig-Sandrow, e Introduction to Statistical Field Theory, do Bresnan. Devo continuar em inglês ou português? So I'll switch to English for physics. Okay, very good. So today I'll give an overview of the kind of models that we'll be studying. And the first type of models that we'll be studying are so-called random walls. So a random walk is a walk where we start at a given point and then we randomly move until a final point. We say some probability of giving a step in the direction r, step r. This probability will typically be described by its moments, which are, for example, the average, the average when I integrate this probability over, say, R nu, for example. Or the connector moment C2 nu, which would be the average of R nu minus the disconnected average of R nu times R nu. Okay? Whereas that one would be just this average here. We would subtract the 1-point function. But this guy, right, by symmetry, this moving to the left or to the right could be the same. So this average could be 0 or not. So this average will be not equal to 0 for what we call a biased walk, but it will be equal to 0 for an unbiased walk. So we already have here two different types of walks, biased and unbiased. See that in random walks there are at least two types of walks. And here in this picture, you see that I had a walk, and here we have an intersection. And this intersection could be allowed, and then we are in what we call the usual random walk, or unconstrained random walk, or it could be forbidden. And if they are forbidden, we are dealing with saws which are self-avoiding walks. This would be relevant if I want to study, for example, polymers. I have some big molecule that cannot self-intersect because it occupies some space, so it cannot be on top of each other. Okay. These models could be in 2 dimensions, like in the picture, or in any number of dimensions. So that's a class of models that we could describe. We have unbiased, biased, self-avoiding walls, or usual random walls. We already have like 4 categories of models we could study. Any question about this type of models, or about what they are, and so on? Have you seen them before?
Most of them.
Did you study any properties of these models? Tell me something you know about these models.
I think only the unbiased wall.
Okay, unbiased wall. And what do you know about the unbiased wall? Something.
The average is 0.
Yeah, indeed, the average is 0. So for this unbiased wall, if I compute, say, what's the average displacement after n steps, it's 0, because it can go to the left or to the right. What else do you know?
The expectation value square minus the expectation square. I don't remember the name of this. It's covariance, I think. Is a Gaussian.
Okay, so that's one thing. The other thing that you are pointing out, indeed, we'll see this, and you are saying that there is some Gaussian behavior. Indeed, we will see this. We will see that these are described under very general circumstances by Gaussians. This will be still today about the probability of going far away. So we will have a Gaussian behavior at large distances. More things. Do you remember more things about this model?
I remember that in the usual random walk, you could Fourier transform the probability in order to have like delta functions, but I don't remember their names.
Very good. So we'll also encounter, we'll use Fourier methods for finding these probabilities after n steps being at step I. And indeed, we'll recap some of these things, and that we'll probably do still today. But then we'll do more. We'll see what about the biased one, what about the self-avoiding walls, and we will also review those things in the context of statistical field theory. We'll see in the language of statistical field theory, what does it mean that we have this Gaussian behavior? What does it mean that, what's the physical meaning, the geometrical meaning, or the physical meaning of these Fourier transforms? And as we'll see, they have a nice interpretation in statistical field theory. Maybe let me not hear. You lost random walk.
It will be recorded, so
Yeah.
This is being recorded here. Oh, okay, great.
Okay.
I'm sorry, did you already talk about like the how the class is going to be graded and how it works and all of that?
No. Very good. Second type of models that we will be seeing. So that's the first type. The second type are spin chain type models or spin models. Which can be spin models or can be something else, but I'm calling spin models everything whose variable is some spin Si, classical spin models. And let's define them. Let's say, what is their partition function? Partition function is what? It's the sum over all configurations, e to the minus beta times the energy of the configuration. And let's suppose this spin, the simplest model, this spin will be continuous. Then I integrate over the spin from minus infinity to plus infinity. And I do it for n spins. This is the definition of my model. I integrate over each possible spin, and then I could have e to the minus some sum over neighbors. These are the neighbors Right? So I and J are spins. They can be in a lattice, for example. Right? It can be an L by L lattice. In that case, n is L squared. And there is some interaction between neighbors. And then, say, spin I can interact with spin J with some strength Aij. And there could also be some magnetic field. So we could also have sum over I, magnetic field with strength Hi at site I. Now this model, defined in this way, is called the Gaussian model, because it's just a Gaussian. This could be the model that we would use if we were to describe some spin system where the spin is large. Like if the spin is 5 halves, right? Then we have 6 states. 6 states is like infinity, so it's really not so bad. Right? We could have another model which should be the same weight, but instead of integrating, we would sum over the spins, whereas one could be, for example, plus minus 1. That's the other extreme. And the sum of Sn equal plus minus 1, and then exponential of the same thing. And this is called the Ising model. This would be a model if we are having interaction of particles whose spin can be up or down. That's another example of some model that we could consider.
Yes, in what sense this is classical? The Ising model, for instance, that you said.
In the sense that in all these models, what we are doing in code, we are computing a partition function, which is the sum over the configurations e to the minus beta times the energy of that configuration. Right? We are summing over configurations and the fluctuations are terminal. Right? Beta, here I did not write explicitly, is inside A and H. Just absorb it there. But there is no time evolution, everything is Euclidean, and I'm just averaging over configuration, and that's what we'll do throughout all the course. Now, of course, there's no big difference between Euclidean and Lorentzian if we rotate between one another, and indeed there are connections between statistical field theory and usual quantum field theory that we can get by weak rotating. But we will always stay in Euclidean field theory doing averages weighted by some temperature. Okay, so fluctuations are terminal. Good. We could also have some model which would be in between these two. Okay? We could also have some model which should interpolate between these two, where we will say add here if I add here minus V of Si, suppose I add an extra potential, then it's not the Gaussian model anymore, but say this potential here, suppose it's something that could be like this, and then, so this would be when you have some parameter G big, and it would become just a Gaussian when this parameter G is very small, with some particle with some parameters, right? Then see, when the parameter is very small, here, when it's just a Gaussian, it's doing nothing, it's just redefining A, right? So here, this is just a Gaussian, this is just a parabola. So this is just redefining our A. So it's doing nothing, right? It's the same model, it's still Gaussian model. But in this case, what happens in this potential? In this potential, what happens is that the configurations over spins that could take any value, now they want to take values here or here. Configurations that are in the middle are very much suppressed. Right? So in practice, in this case, if this distance, say, is 1, then in this limit, s is effectively plus or minus 1. And so we go back to the unknown. So that's how we would consider a model that would interpolate between the two. And you would ask, is there a big difference, for example, between this potential and the exact discrete sum? Is there really a difference? Does it make any difference in practice? That the spins are either exactly discrete, plus minus 1, or they are continuous, but in practice they can only be either here or here. And the answer is no. From very far away, at low energies, the spins in this situation, they go either to this position or to that position. And the only this model would be basically the same as this one, and the same in the sense of universality, which is the sense that at large distances they will give the same physics. And it had to be like this, if there are no exact. Otherwise, it will depend very much on the microscopic realization of the model. Okay? So this is how the model would interpolate between Ising, or let's call it Ising-like model, and Gaussian. But we will see better how this Ising-like is Ising in practice. Okay? We will study this a little bit more in a few lectures. Another model that we will study quite a bit. So this is Ising, this is Gaussian. Another one that is a very important one is called the spherical model, where we have the integral over spins that are now vectors, S1, D, Sn, e to the minus, now we have Si dot Sj, there could also be some matrix, Aij, or typical in this case, this is already interesting enough, this is just a number A, but it could also be a matrix, doesn't matter. Okay. Minus Hi dot Si, sum over I. But then the spherical model is one where we impose that these S's have unit length. Okay. So we impose that these S's have unit length, where these S's, as I said, are n-dimensional vectors. Okay. And this is the statement that each of them is a unit vector, so each of them is a vector of length 1 in the dimensional space. And this is what is called the spherical model. And finally, as a last model, let me write it up here, we would have Z, which would be the same as the spherical model, ds1, dsn, e to the minus, the same thing as the spherical model. But then, instead of putting these delta functions, we could put again some potential V for Si squared, where this V would tell that the modulus of this Si squared needs to be more or less 1. But now we will think of this potential as kind of a, because it's our vector, let's say V of Si, where this potential is like this Mexican hat that says that Si wants to have unit length, so it wants to point somewhere here. But there is a line of minima rather than just two minima. So this is a little bit more interesting than here. Here you are stuck either here or here. And here is a Mexican head, so without any cost you can go around and rotate along this valley and go around any point in the minima of the Mexican head. So this will be this maximum. Right? And this model would be called the ON model. Because it has ON symmetry, which are the rotation and descent vectors. Okay, so let me. Right, we have ON model, Gaussian model, spherical model, ionizing model. So we have these four models, plus the random models we spoke about already. And what are the type of questions that we are most interested in when we want to study the statistical mechanical models from a statistical field theory point of view? We are interested in long distances, in large distances, in what's the emergent behavior as I look at a big table full of spins and I probe two spins that are, say, very far away. So what we are interested in is not in the particular microscopic details, but on macroscopic emergent quantities. So let's talk a little bit about large distances. So that is about these indices I and J that appear in these formulas. They could be spins on a line, say. This would be one dimension, right? But they could be also spins on a lattice, right? And then the neighbors would be, then each guy would have four neighbors, right? And this would be 2D. Or it doesn't need to be a square lattice, it could be, say, a triangular lattice. And then each guy would have, for example, 6 neighbors in a triangular lattice. And this would also be 2D. And we could have a cubic lattice, etc. And this would be 3D. And we will be studying the dependence on dimension of many of these models. And the kind of questions we want us to consider, say, a big table. And to have 2 points separated by some distance r. And ask, say, what's the correlation function between S at position r dotted with S at position 0. Right? For example. That is, are they aligned or are they typically random? Right? And this comes, of course, from originally there was no such variables. All we had was S with index I and S at position J. So we went from a discrete variable to a function of a continuous variable that's a field. Right? It's S that now depends on a continuous label on the table, because as we zoom out, we don't see the lattice. We are coarse-grained and we don't see the lattice, we only see the long distance properties of the material. Okay? So this would be a decomponent field. So this gives you a flavor of some models that we will describe. Now these models, I describe them as spin models, but that's just a name. They might not describe spin models. For example, this ON model was a vector in d dimensions, right? So it's a map to 2D-dimensional space. So these models, for example, where you have at each point a vector in d-dimensions, show up, say, in string theory when we want to describe strings moving in d-dimensional space. They are called sigma models. But they don't need to be spin models. the model where I said that I have some interaction between continuous variables at position I and j could be displacement of some lattice positions. And this could be describing some material, and the fluctuations would be defined by phonons of the material. It doesn't need to be exactly the same models. And that's a very general thing that I will mention in a minute, which is this notion of universality, the fact that in statistical mechanics, the same models describe very, very different physics. So let me just make a list at the third, that there are other more exotic models. We could have, for example, interesting statistical mechanical model where we have gases and particles. I put many particles in a room and I have a gas of particles. Right? So we could have some gas of particles. It could be, for example, an interesting one, for example, is a 2D gas of charged particles. That's the Coulomb gas. I put two particles in two dimensions and they are interacting electromagnetically with each other. And we could study what's the statistical mechanical properties, what's the physics of this model. We could have interesting models that describe growth of crystals or growths of surfaces. So we have interesting growth models. We have, for example, the roughening transition, which is a statistical mechanical model that studies some surface that can be either very smooth or very random. And there will be a transition between the two, in the same way that in magnetic materials there can be a transition between ferromagnetic and antiferromagnetic behavior. Other models that are very interesting are conformal field theories, models that don't scale fixed points. Models that describe percolation, like when you have a rock and you want to find whether there is a path in a porous material that goes from one end of the rock to the other end of the rock, so that you can extract oil from one end to the other. So those will be models of percolation. We have matrix models, where the variables are not vectors or scalars like the ones I described, but matrices. And these matrix models, for example, they show up also in random surfaces, in string theory. They also show up if I try to study these spin models, but if I try to study spin models that are not on a fixed lattice, but are on a random lattice. So suppose the lattice itself is random. That could happen, right? I mean, I could have a bunch of magnetic materials. I throw them into a spin glass, I cool down the system, and then once it's cold, the spins are all randomly connected to each other, right? So these spin models on random lattices. This is also very interesting, and it's actually related to these matrix models, and I hope we'll have time to mention a little bit of that. And for example, more recently, people are studying these SYK-like models, which are Fermion models with many degrees of freedom. They show up in condensed matter material of high temperature superconductivity, but also in examples of two-dimensional holography. So we could have SYK-like models, and they are also quite interesting. And we might touch upon some of them, but definitely not all of them, and it will also depend a bit on the kind of questions you ask. I might choose to go in one direction or another. Okay. So now I'd like to conclude this general introduction with a few general comments. But maybe before, let me ask again for questions. Or maybe let me first ask the same question I asked before when I saw the random models. What about these spin models? Are they familiar to you? Have you encountered these spin models before? Yeah? Which ones? All of them? Some of them?
The Ising model.
Ising model.
Like,
What do you know about the Ising model?
I've treated it with mean field theory and Ginsburg perspectives.
Okay, so mean field and Landau-Ginsburg. Did you study the exact solution of the Ising model in 2 dimensions?
The Unsucker solution?
Okay, that's something interesting. I think it's cute to know. So we'll try to see how can we solve this model. Sometimes we can solve them exactly. We can compute the partition function exactly. And sometimes that's useful because having an exact solution at hand, we can test many of our intuition. We can develop intuition. Sometimes it's not useful. Sometimes it's just to show off. We can also be able to solve it. Say if you solve the Ising model on a given lattice, you learn a lot. Then you solve in another lattice. Okay, you check that some things are universal. For example, that maybe for some physics it doesn't matter what the underlying lattice is. Right? But then, once you understand that, if you study it on a 3rd lattice, then it's an example where, okay, it's nice to solve it, but who cares? Right? And so, there's always this tension between when we have exactly solvable models, it's great, we can develop intuition, but we should not exaggerate. The goal is to learn physics, it's not to just show up. What else do we know about this Ising model? So the one-dimensional Ising model, for example, have you seen? Did you have any statistical mechanics course before? You did, right? And you?
Yeah.
As well?
I did, but for basic level.
But Ising model in 1 dimension, no? So only gaseous particles in a room. You integrate over the positions of the particles, and you derive a PV equal nRT, and these kind of things. That I will not, probably not touch upon in this course. What about the one-dimensional Ising model? Did you encounter it? Yeah. So that's an example of a model that can be solved exactly. Because the variable I just couples to I minus 1 and I plus 1. And then the variable I plus 1 just couples to I minus 1 and I plus 2. So if you change variables to the link variables that tell you that if the link is of the same sign or opposite sign, each link just appears once. So you can just do the sums exactly. You just do the sums and you get the result. So that's a very nice exactly solvable model that we will study at some point. Okay, let me then make a few comments on this, on the logic of what we are going to see. One is that in all these models, we see that we have a rigorous microscopic description where we have a finite number of degrees of freedom. We have like n spins with neighbors and we sum over the possible configurations. Or we have a random walk where at each step I have some probability of moving. Right? So we have an underlying like this. We have an underlying microscopic description. And having an underlying lattice means that if we are careful, we cannot have any UV issues. If we have UV issues, it's because we are being silly and we are not understanding what we are doing. Right? There are no infinities, right? Everything is finite, so there should be no UV issues if we do things properly. Second general comment is that we'll be encountering a lot, we'll be studying normalization. What is normalization in this context? It's zooming out. It's just coarse graining and looking for long distances, what are the effective degrees of freedom. Right? So again, it's just a question of asking about large distances, no infinities, whatever conceptually is to be understood about normalization, we should be able to understand it very precisely. The third keyword that we will encounter a lot is the idea of universality. That is related to 2 key things, 2 very important different things. So one thing that it is related to is that large distances are insensitive to many microscopic details. And this goes to this idea, so technically, this is related to this idea of normalization. And it's related to something we'll be seeing a lot, which is the idea that there are effects that can be relevant or irrelevant effects. And the ones that are relevant effects are the ones that if I do that small change in my model, the large distances will be different. And the ones that are irrelevant are modifications to my model which don't affect the large distances. And the good news is that relevant effects there are just a few, and irrelevant effects there are infinitely many. So whenever you have a given model, there are infinitely many ways of changing the microscopic details that don't change the large distance physics. But there are only a few that you can even count that affect the large distance physics. And that's great news, because then if we can characterize these relevant operators, we can study the large distance physics and realize this notion of universality and the fact that large distances are insensitive to many microscopic details. Okay? That's a very powerful thing, very important one that we'll be seeing. That's just one instance of universality, this idea that large distances are insensitive. The other manifestation of universality, which is related to that one, follows in a way from that one. It is only possible because of that one, is the idea of dualities. It's the idea that many different models have same large distance physics. So let me give you, and this is related to the notion of duality between models. We say that two models are related by duality if at large distances they have the same kind of physics, even though they might look very different. So let me give here some spoilers, some examples that we'll see throughout the course. Okay. So now that we know the name of the models, let me tell you. For example, the usual random walk, the usual unbiased random walk, is related to another model that we presented. Can you guess which one? That's an example of two models that in a way at large distances are describing very much related physics. ON model was the guess. Wrong? Another guess? It must be a simple model, right? Usual random walk, you just randomly move around. So it must be one of the simplest of the other models. Ising? No, even simpler than Ising? Which one is even simpler? It's the Gaussian model, where it's just abundance and Gaussian. So they look very different, right? One is a model of a random particle that moves around. One is a spin system, where spins can take continuous variables, and we will see a nice relation between the two. Then we have self-avoiding walks. They are also related to a model that we presented in the second Which one? You guess?
Isaac one.
No. Well, it's hard to tell you will not guess, because it's really a beautiful and subtle case. It's the ON model. I remind you that in the ON model, we have our vector S, which is an n-component vector. Right? So it describes an n sphere. And in a self-avoiding wall, there is no n. Right? And in the ON model, there is an n. It looks weird. So it's the limit when the number of components goes to 0. It's a very strange limit, right? The vector disappears. So you have to solve the model and then analytically continue the number of components to 0, and that's related to the self-avoiding wall. And we will also see why in 2 lectures, probably. Then we have, say, the 2D Coulomb gas, for example, a 2-dimensional gas of particles. I just have a bunch of particles interacting with the Coulomb gas. And that is also related to a model that we have seen before. Can you also try to guess? That's not rising. It's the O n to 2 n equals to 2 model. It's the model where I have a bunch of spins that have 2 components. In this case, 2 I don't need to analytically continue. I can say it's O n equals to 2. 2 is an integer, it's a good model, and it's very neat if they are the same universal with less once again. So you see, this gives you an example of so these things as I see now, they are not familiar to you. This is one of the main goals of this course, is to exhibit these dualities and understand how they work. So one more general comment is the notion of order. Order is a very important concept in statistical mechanics. And we would say that we have order if we have the following. Suppose I have my table, and there is a big region, a big macroscopic region, where inside this region the spins S are roughly pointing in the same direction. Right? So they are roughly pointing more or less in the same direction inside the big region. Then I would say that I have order inside that region. Okay? This would be the synonym of order. And we see that this kind of scenarios is very D-dependent, where D is the dimension of space. Right? We saw D equal 1, D equal 2, D equal 3. And there are many things we can say, very general things, about whether these kind of things can happen or not, without specifying the details of the model. For example, we know that magnets exist. So there are pieces of 3-dimensional material where the spins are all pointing more or less in the same direction and they form a macroscopic magnet. But you have never seen a 2-dimensional material which is magnetic, which has an order. And that's because that's not possible. In 2 dimensions you cannot form order, and in 3 dimensions you can form order. So that's something very general that you can understand. Why magnets exist as a chunk of 3D material, they could not exist as a layer of 2D material. Okay? So this will be able, this is another thing we'll see. So 3D magnets exist. 2D magnets do not exist. That's something we know experimentally, we know it. Finally, one last comment that's kind of a triviality is that exactly solvable models are useful. And we will see a bunch of them, like the 2D Ising, the 1D Ising, even simpler. And they are useful to develop intuition, to develop or test intuition. Just to give you an example. Now it's something obvious that we know very well from kindergarten, that there exist phase transitions. That a material can change the temperature and suddenly jumps. But for a long time, people wondered, does it exist, or it's some kind of, do we have a transition which is abrupt between two phases, or it's smooth? Right? If I could solve the model exactly, will I find that it is smooth, or will I find that the function really jumps abruptly? Are abrupt jumps something that exists in nature, or things are smooth and dot? And I think it's fair to say that it was when people solved exactly the 2D Ising that they saw, yes, they jump. Because until you can solve it exactly, you could think, well, that's because of my approximation. If I were capable of really solving the model exactly, I would see that this phase transition is smooth and it doesn't exist. Now, of course, I'm talking about in the limit of large materials. If the material is finite, with a finite number of degrees of freedom, you cannot have any phase transition. Okay, so that gives you an idea of, with these general comments and this survey of the space of models that we'll be playing with. This gives you an idea of what the course is about. And do you have any questions about this or comments before we go and start studying the first class of models, which are these unrestricted random walks, biased and unbiased. It's funnier for me if you interact. If you don't interact, I'll fall asleep.
I actually have a question regarding like the field theoretical part of the course, like how much quantum things do we have to know?
Mathematically, there's no big difference between Euclidean thermal field theory and Lorentzian quantum field theory. It's just with rotation of each other. So we will be using techniques from field theory. I'll be teaching, for example, probably some introduction to Feynman graphs that will show up in statistical mechanics. They also show up in Lorentzian particle physics. And it's technically the very same thing, but the way they appear is a little bit different. So we will not be doing any quantum explicitly, but the mathematics and the physics we'll be seeing is exactly the same as the physics and mathematics we will see in the quantum setup.
But there are not like prerequisites. I mean, you'll be teaching that to us.
Yeah, I think so. Okay. Good. So we start with random walks. And yeah, so the purpose now is to study random walks. So, as we said in random walks, we have some probability at a given step of moving by a vector r, and that probability could be many things. Let's give here a few examples. So one example could be, for example, that 1 over 2d, if we are in d dimensions, it could be 1 over 2d, which are the possible directions I could go, if I move in this direction. And it would be 0 otherwise. So I would say that the probability is 1 over 2d and 0 otherwise, where this distance here would be, I don't know, it's up to us to define the unit of length, but we could say this is A0, a typical step size. It could be, for example, so these are a few examples, it could be that the particle can jump in any direction provided that direction is a distance A0 away, for example. And in this case, we should divide to make sure it's normalized by some area, which in 2 dimensions would be something like 4 pi A0 squared. But we will divide some area to be normalized. Or it could be, for example, some Gaussian, e to the minus r minus some r0 squared over 2 sigma 0 squared, etc. There are many other examples. Which of these is biased? And which are unbiased?
The first one is biased.
Which one?
The first one.
The first one is biased. Why?
You force them to walk in a specific direction.
Maybe my picture is misleading, but so this is 1 over twice the dimension, right? And then, so in 2 dimensions, it's 1 over 4, and I can move up, down, left, right. And in 3D, it's up, down, left, right, front, back. The last one is the one which is biased because it has an average R0. The average is not centered around R equals 0, it's an average around R0. So this one, for example, here is biased. In this case, we have that the average of R is equal to this R0. And you could actually also compute the second moment that I defined, C2 mu nu. And this would be delta mu nu times sigma 0 squared. So these 2 moments, the first moment would be R0, the second moment would be the average displacement would be sigma 0 squared, so sigma 0 would be the sigma 0 squared. And whereas these 2, they are unbiased. And they have average of R equal to 0. Notice that we could also have another example would be the probability being something like 1 over a squared plus r squared. It's already seen. There's a probability of going, it decays harder and harder to go to larger distances, like in the Gaussian, but it decays much slower. And this distribution is kind of interesting on its own, that this one has infinite moments. What is different? That's very different from the other ones. From these ones, you see that all moments are finite. Right? Because any integral of a polynomial r times a Gaussian converges, and any integral of a polynomial r over a function that has finite support converges. for Lorentzian, already the second moment is infinity, right? It doesn't converge by multiplied by r squared, right? So this one is infinite moments, and indeed we are not going to study this. There is interesting physics on these blocks, but this is already a type of model that is interesting, but we will not study it.
I'm sorry. I have a question regarding the biased one. Can't we say that, I mean, morally it is unbiased because studying it would be the same as at every moment if as studying the Gaussian distribution but center at 0, and every time the observer is the one that moves in minus r0? Like at every step of the walk, like relative to an observer with a velocity which is r0 divided by 1. In the opposite direction, it is a Gaussian center at 0.
The answer is no, as will become clear soon, but let me see how I can explain right now before what I'm going to do next. Depends what you call equivalent. If you say that these models describe polymers, right? Which means that you simulate these random walks, and that's a configuration of a polymer. And you do it many times, and you get typical configuration of polymers. Right? Then what questions can you ask? You can ask, for example, what's the fractal dimension of these polymers? Do they go, are they aligned? Are they Brownian motion? What's the fractal dimension? That fractal dimension is 2 for this and 1 for this. It's a really different thing. Now, you can ask another thing, which is, given a picture of the polymer in this setup, can I do a mathematical transformation that maps me to a polymer of this type here? And that might be true. But I don't know. I doubt it is actually. Okay. So, but you can ask me this question soon when I will be finishing the analysis of this bias. Okay, now what are we going to do next? Now next we are going to do a normalization of the random walk. By the way, since you arrived late, I forgot there is a page here with some more. Okay. So, let me tell you what is our goal. Our goal is to ask, what do I see when I zoom out? Right? So I have my random walk. 1, 2, 3, 4, 5, 6, 7, 8. Right? 8 steps. And then I do 8 more steps. 1, 2, 3, 4, 5, 6, 7, 8. And then 8 more. 1, 2, 3, 4, 5, 6, 7, 8. Etc. So I separated in blocks. Now, what would be the normalization? The normalization would be to say that I take these n steps, so this is 1, 2, up to n, and I take this point and this point, and I just join them directly. I say I replace n step by an effective big step, right? And then I take this step to this step, and I join them. And then I take this step to this step, and I join them. Then I take 1, 2, 3, 4, 5, 6, 7, and And I would go from this to this, and that's what we would call the coarse grain, right? Which is this effect of joining, redefining what I call my fundamental step. And this is step 1 of my renormalization. I want to say that I don't care so much of the molecules in my polymer, I want some more macroscopic step. My microscope is not that good, so why do I care about such tiny steps? I want to do like 100 steps at a time. Right? Now you see that if I do this, it's a bit unfair to compare the first picture to the second picture, right? Because imagine you have a huge random walk in your screen, right? And then you just do a huge renormalization step. Then it looks like a straight line. Okay? But that's not what we should do. What we should do is we coarse grain, and then we say that this is my new fundamental step. Right? I want this to be the same size as this, so that I compare what happened after I zoom out. So as a step 2, I rescale this such that these steps have the same typical size as this. So I rescale, and it looks like this, then like this, then like this, and like this. Right? And this is what we would call step 2, which is we renormalize to be able to compare. And this was my unit, and now this is my unit again. Right? And then I ask, now this path, is it the same as this? Does it look like this, or does it look different? And that's what the effect of the normalization will be. As I zoom out, and I consider that my new unit, I don't measure in nanometers, I measure in millimeters. How do things change? How do my couplings, when I was studying nanometer physics, change when I study millimeter physics? Right? But in my screen, my unit is now this. This is my microscopic unit. Things that happen below this scale, I don't know. They need to be taken care of by some effective parameters. Okay? So this is our starting point. This is after step 2, and then we repeat this many times, and this would be the idea of applying the renormalization many times. That's the renormalization group. It's this subsequent application. But it's crucial. In this example, we already see that in renormalization, it's not about just coarse graining. It's not just about renormalizing. It's about both. Right? If you don't do both, you are not studying. I mean, you're doing something a little bit silly, right? It's like you have your screen, you coarse grain, and now you say, I only have like 3 steps. You know, you have to zoom out so that it looks similar.
When you have a chain, you have interaction between first neighbors, but the couplings are different. So you take the coupling with the largest coupling and try to renormalize, and you have an effective coupling. So you try to do something like this.
It's exactly like this, so we will see it. We will study that in detail. But that's what we do in usual renormalization of spin systems. What do we do with spin systems? I look at many spins in my lattice, and I say these 4 spins are what I'm going to look at. My microscope only sees the 4 spins as 1 pixel. So it only measures the total spin of that block of 4. Right? So the first thing of zooming out is saying these 4 spins are replaced by 1 variable. It's the analog of joining these n steps into just 1 step. Right? But then I want to zoom out such that that new block is my fundamental unit. And then that fundamental unit interacts with the other fundamental units. And you ask what are the rules of the game for that fundamental unit then. Okay? So it's exactly the same thing, very important thing. We have these 2 steps. Okay? Good. So, let's work this out. Let's start with step 1. Let's do step 1 and then step 2 for the random walk. Step 1. Step 1, we want to ask, what's the probability for being at position R prime after n steps? I know what's the probability for one step. I want to give n steps and ask what's the probability in n steps of going through a distance R prime. So what is it? Well, I do n steps. So what do? I have to integrate over from product from I equal 1 up to n. Each step I move by a distance Ri. In total, my distance R prime is the sum of the Ri. Right? And each time I give a step, I have my probability for my Ri that I start with. We should put here a prime. It's not the same function. It's what's the new function, probability prime, right? After giving n steps, and that was the probability for my fundamental step. Now this is equal. What would you do now? Next step. Very good. Fourier transform, or in other words, we write a representation for the delta function. The delta function is what? Is the integral d is these number of dimensions q over 2 pi to the d times e to the I q times this, that I will split into r prime. And then there is e to the minus I times this. And I combine each exponential with the corresponding probability. Right? But then I get just average of e to the minus I q dot r to the power n. Is this good? Too fast, too slow? You see, no more integrals over r, because now after I do this trick, they factorize, and I get dr1 e to the minus I q r1, probability r1, that's just the average. Same thing for r2, that's just the average. Same thing for R3, that's just the average. So I just get average to the power n. Now this quantity here is equal to e to the I, or e to the n. So now you can just expand this out and compute the average. For example, if I expand out, I get 1 minus I q average of r plus q squared average of r squared plus q cube average of r cube. And then I can put it back in the exponent, this average. And when I put back, what happens that I get connected averages that are exactly the moments we defined before. Okay? So we get e to the in minus I q dot expectation value of r minus 1/2 q mu c2 mu plus order q cube why we are stopping at order Q is because if we are interested in large distances, large r prime, this is equivalent to small momentum q, and so these terms will be subleading compared to this, and we will check in a second that this is a good approximation. And so these terms here would be negligible. Whereas these first ones, the Gaussian and this one, would be important. I remind you, okay, good. So this is equal to R0 by definition. And this thing, that we define it as sigma squared as the moment of the distribution times delta mu. That's the definition of this sigma and R0. But now, the integral over Q is just a Gaussian integration, right? So you can do this integral over Q. And therefore, you get, once you do the integral over Q, and when you put back the normalization for all the, you don't put back anything, you do the integral over Q. And you get the following result: 2 pi n sigma squared to the power d over 2 exponential of minus r prime minus n r0 over 2 n sigma squared. That deserves a box, so let's put the box. The box is this: probability after n steps is equal to. So there are a few things that we should say at this point. So first, this is the Gaussian that we spoke about in the beginning, right? We had mentioned that there was some Gaussian going to appear, and indeed, here is this Gaussian. And so we observe here that if we do n steps, right, eventually what happens, it doesn't matter which distribution you started with. After you zoom out a few times, it looks like your walk is moving according to a Gaussian distribution. You could have started with a discrete distribution that you just jump from neighbors. But after you course grain a few of those steps, it's a Gaussian. You could have started with any distribution. It could be e to the minus absolute value, and it would become a Gaussian. So this is an example of universality. Doesn't matter what distribution, what are the details of the distribution you start with. You flow, when you say flow, meaning when we go to large distances, we flow to the Gaussian. Okay? Independent of the details. So let's write those comments down. I don't want to erase this picture though.
Sorry, why can we assume that the C2 is diagonal? In the units?
Yeah, so right. So so this C2, the question is why C2 diagonal to C2. I defined it as average of R mu minus the disconnected average. That's also the same as the expectation value of R mu minus the expectation value of R mu times the same thing for nu, R mu minus the expectation value of R mu. So it's really the fluctuation around its mean value. And here we are saying that after you subtract the mean value, all directions are isotropic. But they don't need to be. There could be not only a bias, but there could be some anisotropy. There could be some metric. And then that metric would show up in doing the integration, and it would show up in what we call this distance squared. The metric would appear here in contract in making this distance squared. I forgot to square it. Okay. But here we are assuming isotropy. We are assuming there is some wind, but apart from this wind, things are isotropic. Right? You don't need to be, right? It could be, the probability could be like 45% chance of going to the left, 45 going to the right, and then 5 going up, 5 going down. Right? Then, what would you do in that case? You would rescale what you call x and y, or if you don't rescale, then here it appears component x with coefficient, and then component y with a different coefficient. That's just a metric that would measure distances differently in those two directions.
I'm sorry, but in that formula, then it does appear that mu and mu are completely symmetric, right? Because products here are commutative.
No, they are symmetric, but it doesn't need to be equal in all directions. Right? Your probability could be different in x direction or y direction. Right?
I'm sorry, mu and mu here, r mu is it's r in the direction of mu. Yeah, okay.
You are the
Okay,
components, right?
okay. Yeah.
For example, mu could take 3 values, but perhaps the wall just moves in 2.
Okay.
Then,
Yeah.
of course, we won't get C, right? Because the path doesn't leave the plane. Okay? So when we say this is sigma squared delta mu nu, here we are assuming isotropy. Okay, but then let's make a few comments about the fact that we got this Gaussian here. So what words would we say here? We did a coarse graining step, and we got a Gaussian. Doesn't matter what distribution we start with, we have this Gaussian. So the first statement is that this is the law of large numbers. Which in this case translates into this universality. And the universality says that all distributions flow towards the Gaussian. Now, well, all distributions with finite momenta, for example, because we already said that it's Lorentzian excluded, for example. The second comment we will make, this is one comment. The second one is that, let's say it's unbiased. So we conclude that unbiased random wall with m steps of size, of typical size sigma, is equivalent to a random wall where we give m over n steps, because each n steps we coarse grain into one step. But what's the effective size that we are getting? With effective size of size square root of n times sigma. Right? Sigma squared we can multiply by n. Now, here you see that the step changed. This was this thing. The step was unit, and here the step is square root of n times unit. We see now. That's not what we want to do. We want now to do step 2 and rescale such that that new step is again unity, so that we can compare the walk before and after we cross train. Right? So step 2 now. It's a pity I cannot use those blackboards. It's very annoying. So this was the probability in this box. And now we do step 2, which means I redefine my r prime to be equal to square root of n times r. Because when I do this, then my average step size becomes 1. And now my probability prime of r is what? Is, well, there is some prefactor, we don't care, exponential of minus r minus square root of n r0 square over 2 sigma squared. Because I risked it. And that's my probability for the second picture. If in this picture here on the top I have some probability, in the second picture I have that probability. That's the probability after I did this normalization step. So what do we see in this picture? We see that by definition we didn't change the unit step. So this would be our renormalized sigma square. By definition, because we rescaled such that this was fixed. But this one here was our renormalized R0, and that guy changed. We see two things. We see that if R0 equal to 0, that is for unbiased walks, the Gaussian distribution is what we call a fixed point of the normalization group. In the sense that I start with the Gaussian, I apply this transformation, I get the same function. Exactly the same, not approximately the same. So all distributions flow to the Gaussian, they want to flow there. And if I start with the Gaussian, I stay there. It's a fixed point, it doesn't move. I'm not moving towards the Gaussian, I'm at the Gaussian and I stay at the Gaussian. Okay. And in fact, for the Gaussian, you could do the integrals explicitly. No need to go to Fourier, nothing. You could just write the integrals, do them, and you will see this result. Okay? So in the Gaussian case, we could do the previous integrals analytically. On the other hand, if R0 is not 0, we see that R0 is relevant. By relevant, it means that it grows. There is a square root of n here. It grows. Whereas all higher moments, C3, etc., are irrelevant. They just go to 0 until you get the Gaussian where there is only the second moment. they decrease under the RG. You start with a distribution that has higher moments, and they go to 0 to the Gaussian that only has the same amount.
I'm sorry, can you comment a little bit more? I didn't ask when we did it because I thought it was stupid, but now I see that it was very important. There was a step in the derivation where you expanded, we wanted to calculate the exponential, the average of the exponential,
Yes.
and then we expanded up to second order in Q.
Yes.
And the reason was that for large R prime, Q is small. But we were integrating over Q over all possible values of Q.
Right, but when R prime is small, the region of integration is dominated by the small q. Because when R is large and you integrate over Q, R is large, you have a phase in the exponent. So if Q is large, that oscillates like crazy and it's 0.
Okay.
Right? That's the usual thing with the phases. If you have an integral, e to the iqr, and R is large, if Q is large, you are oscillating like crazy, the area is 0.
Okay.
So only when Q is small, the function is changing slowly and you have a chance of capturing any area.
Okay.
And that's why that is the usual thing. Large distances is small momenta, small distances are large momenta. That's the physics of it. Okay, good. So what's going on in a, let's see how all this is very, how this is very natural, this R0 in pictures and in an equation as well. Actually, this example is good. This example here is kind of good. This here, the way I do it actually, because the blackboard, because we are used to writing from left to right, this looks like a random log with bias, right? It's kind of moving towards this direction. It's more of a random, but it's kind of moving to the right. So you see that we start like this, it intersects a bunch of times, but here it already doesn't intersect, for example. And then, if we do another RG step, it would start to look, two steps, it would start to look like this. It would be even flatter now. And then if you do another one, it starts to look like this. It's almost flat, and then you go on, and eventually it's just totally flat. So that's what you get if you start zooming out something that has a bias. So this line here, what I'm drawing here is zooming out several times with bias. As you zoom out with bias, you see more and more that there is some wind. Right? In other words, if you are in the middle of some cloud that's moving chaotically, and you are zooming in very closely, you cannot tell if there is a wind pushing them. You have to zoom out to see that this big cloud is moving. Right? And here it's exactly what happens. So as we zoom out, this effect of R0 is the most important, to the extent that at the end, when I really zoom out, I only see this R0 moving my particle in a particular direction. But as I zoom in, when I'm looking here, I cannot really tell if there is a bias if I just look here. I can only tell as I start zooming out and seeing that the picture is moving to the right. Okay? So let's see this let's draw a picture first and then let's see this in formulas. So what I'm saying is that we have R0 equal to 0, and that's a fixed point. But if R0 is not 0, it grows under zooming out, under the RG, and we put an arrow to indicate that it grows. And it grows to R0 equal to infinity. So this would be the UV. I start with a very small R0. I almost don't see this bias. And I'm zooming out at large distances. I go to my IR fixed point where this bias dominates because it's a relative deformation. If I start with strictly zero bias, then I stay at my fixed point. But my fixed point is unstable, meaning that if I open the door and there is a little bit of wind, it changes completely my random particle in the air. That's fine. That's physics. The relative operator are the amount of work, fine-tuning we need to make sure that the large distance physics is the same. In the case of the random walk, we need to make sure there's no wind. So with bias, we get this. Without bias, we would start with a random walk like this. And after we renormalize and rescale, we'll get a similar walk, and then a similar walk, and they will eventually be stuck, and they will be in the Gaussian fixed point. And no matter how you zoom out, if you zoom out and rescale, zoom out, rescale, cross-grain, rescale, cross-grain, rescale, you don't see that things are changing, and you can call it a kind of a scaling invariant setup. Whereas if you have bias, you zoom out, and this bias is increasing. You are describing effective models that have more and more bias. Right? The distribution is more and more biased, to the point that at some point this bias is huge and it's just moving in a straight line. Right? Very good. So let's do one computation, a very simple computation, using this Gaussian, using any distribution. And to make contact with what you said, what's your name? What Carlos said in the beginning about the average distance square of this path. So let's define this quantity R after m steps. And let's define it in the following way. Because the average is 0, like you said, we define it as the average of the square of distance. Right? And this quantity is equal to the following. So how do I do? I expand this square and I write I have I and j, and I can be equal to j or different than j. Right? And then I just, when it's different than j, I get R0. When it's equal to j, I get sigma. So if we do it carefully, this is what we get. I'm going to write, and you tell me. If you want me to do it in detail, we can do it, but it's a very simple exercise. The result of the following is m sigma square plus m square R0 square. For any probability distribution. It's just a question of expanding the square and using the definition of sigma and the definition of R0 that we had before. So what do you see here? You see that this is approximately equal. At large distances, when m is very large, when I do n steps, this term always dominates. And this becomes R0 times m as m goes to infinity. So it's growing linearly with the bias. Right? And this is what we call the IR, the large distances, the infrared. But we could say that if the bias is small, right? If m is much bigger than 1, you did many steps, but it's much smaller than sigma squared over R0 square. Suppose that I have a bias that is small, but you can ask to many steps. Then this term is much smaller than this, so this behaves as sigma times square root of the number of steps. And if R0 is 0, it's always this. It's always square root. So this is the famous result that random walls, they grow with square root of the number of steps. And if you go straight, displacement is proportional to the number of steps. Okay? So this would be the UV. That is, if I am here, if I don't see yet the bias, then this typical distance is square root of n. But when I really zoom out and I start seeing the bias, this typical distance is about the n. When I really see our n star is much bigger than this n here. Right? So eventually I see that it grows with n. When I am at short distances, it looks like square root of n because it's not enough for the bias to accumulate. Okay. And this would be a first example of a critical exponent. If we say that this r, if we define it, if we can say that this thing here is m to the nu, where nu is an example of a critical exponent. And this exponent would be 1/2 for the usual unbiased random walk, and it would be 1 for the biased random walk. And we will flow between a theory. Here we will have in the UV a theory with a critical exponent mu equals 1/2. Flowing in the infrared a theory with critical exponent mu equal to 0. We're at very large distances. Mu equals 1, sorry. Right? Very close linearly with the number of steps. So now, just to conclude with the last statement, to make contact with what Ivan said about bias and unbiased, would they be interpreted as the same or not? And I'll take advantage of this to introduce this notion, a nice notion, fractal dimension. What's a fractal dimension? Do you know? Of an object. The fractal dimension of an object is if you have your object and you imagine covering this object with balls, you have to put balls such that the balls cover the full object. And you ask, how, when the number of balls tends to 0, n of a scales like a to the minus the fractal dimension. For example, you have a line, right? What is the fractal dimension of a straight line?
I'm sorry, what is A?
A is the size of the line. So if you have a straight line, what's the fractal dimension of a straight line? One. Right? Because the straight like 1 over the side. The fractal dimension of a straight line is 1. It's a line, it's 1. So we see that the fractal dimension of the biased walk is equal to 1, because it becomes eventually just a straight line. But let's see if the unbiased one. For the unbiased one, we said the following. We said that we can imagine covering it by a ball which is of the size of the step. This works like this, right? I just put 1 ball per step. And so we have that the number of balls necessary when the step of A, let it be equal to m balls. But then we said that the same path, if I divide by n, what happens here for the step? Right? Remember, if I coarse grain and I split this m, each m I split into n, coarse grain, what's the effect of A? How does A change? It increases by square root of n. Right? So if I combine both and eliminate n, this implies that n of A equal to m, but m is equal to n times n square root of n A. And this implies that n of A scales like A to the minus 2. So the fractal dimension is equal to. And so this would be really something that you could measure. When you do diffraction of polymers, one of the things you can measure is their fractal dimension. And you will see that for the biased and unbiased, you will get very different results. In that sense, we would say that these objects are different. Okay. So next time, we will say that, okay, now I understand about the probability of a random walk. Let me build a generating function that sums over all possible walks. I could imagine that I average over all possible walks, like I have a factory that builds polymers, and I average over all possible polymers. And then we'll start summing over walks with some given average per walk. And then we will see that if we sum over walks that go from position 0 to position r, that's equal to the correlation function of two spins separated by r in the Gaussian model. That's this first example of duality that we were talking about. Yeah? Very good. So we stop. Was it too fast, too slow?